All right. So apologies if you were out there waiting for the live stream. It seemed like it didn't take the first time. Apologies. So here's what we've got. We've got these kinematic equations. Great. This is for the X motion. This is for the Y motion. We can use them at the same time because X motion and Y motion are independent. If you don't believe me, it turns out this is true and we can test this and it has been tested. So now you should believe me on that. All right. Now, what does this end up looking like? All right, let's go to a quick screen share. Not that one. Let's go to this one. Whoops, that's a 2D motion. How about this one? Here we go. Let's check this out. Give it a second here. All right, so the idea here is, in just a sec, you can see here's the ball. And in a second, as soon as I click, I'm going to start this simulation. All right. So what I'm going to do is click right now. And notice this thing is moving downwards. Whoa, it's kind of going all over the place. And let's see. Let's maybe pick some better numbers here. Let's maybe have this be... Let's try these numbers. So the idea here is I'm going to specify the initial position. This is the X coordinate initially. This is the Y coordinate. This is the initial velocity. This is the initial velocity in the X. This is the initial velocity in the Y. And here is AX, the acceleration in the X, and here is AY. So let's watch this thing and check it out again. Whoa, looks like I went too far the other way. All right, maybe I need to, oh my gosh. So let's try that. All right, so there it goes. It's going downwards. It should start going upwards here in a minute. And we may even see it start to go to the left in a minute. Oh, it didn't quite get there. Let's jack up that acceleration. Sorry. And I'm just trying to show you that the equations we were just talking about on my screen behind here basically govern the motion of this thing in some weird trajectories like that. Now you can see it's actually going back to the left. And we could see, if I could start this, look inside the code again, right? Whoops. Right here, notice it starts to the left of the origin, but above the origin. It started out moving to the right and down. And then finally, look at these two terms. Notice that the velocity in the X and the acceleration in the X are opposite. Initially, V initial X is greater than 0, and AX is less than 0. That means it's slowing in the X direction, at least initially. Similarly, look at these two numbers right here, right? V initial Y is negative, but A sub Y is greater than 0. So it's slowing in the Y direction as it goes down. Because again, anytime acceleration and velocity have opposite signs, that's what it's doing. So I just wanted to point out the same equations that we used right here are what I used to code up this simulation. All right. Let's look at another example really quick. Where is it? Oops. Here's a problem right here. Oh, let me clear those annotations out. And so what we could do is look at the velocity and the acceleration. Let's erase this and just shoot this thing. Now, what do you see right here? For a split second in time, this is a different problem. Here's Vx. You can't see that very well. This is Vx. This is Vy. Notice I didn't say initial. These are not the initial velocities. They're the velocities at some point later. So you could think of these as the final velocities after about a second. And notice, what is this thing here? this is the acceleration in the y direction, right? And so when you shoot a ball out of a cannon, gravity is pulling it down. You get this negative acceleration. Gravity doesn't pull left or right, so we don't get anything there. All right. And so we see that the velocities in the x and y, we should see, well, as this ball is flying through the air, since ax is equal to 0, what will be happening to vx as this ball flies? Again, if ax equals 0, what's going to happen to vx as it flies around?
It would stay constant.
Yeah, so let's watch that arrow, okay? So let's see if that's true. That's what we expect. Notice that gravity is affecting the y component, but it is not affecting the x component. In real life, this doesn't seem to be true, but that's because in real life, we've got air resistance, right? So what we could do here is make air resistance a big factor. I'm going to fire this thing again. If we include air resistance, it's going to be very different. Notice with air resistance, you do get an AX. Notice AX is not 0, and now we expect the direction of the velocity, the X component of velocity should be changing. So let's try that. Notice the X component is getting smaller. So air resistance is a big deal. Now, okay, yeah, that's fine. If we had something with a small diameter, like a ball, this would be like a, oh, go ahead. Somebody wants to say something. What is it?
So if the air resistance or the acceleration on the x-axis was great, it would fly back towards you, right? Which is kind of like what happens when...
No, not with air resistance. Well,
say
like
if
with
the
a rocket thruster?
Well, say like that acceleration was strong enough, it would be like, I'm not saying it happens in real life, but if it were like, if you were to throw something and the wind was blowing that hard towards you.
Yeah, that would happen. Yeah, sure. So if it wasn't just still air, sure. If you had wind, it could totally have a large AX, and it could even force you backwards. Yeah. I've experienced such a large wind force. Up on top of Point Sal, it was like 60-mile-an-hour winds, and I literally jumped, and it blew me backwards, just the wind. So that was pretty crazy. Yes, you could totally have a wind force that pushes you back. I guess I was assuming still air, but if you have moving air, absolutely, you're right. Yeah. That was a good comment. Yeah, and notice here, depending on the size of this thing, so 0.1 meters, that's like 10 centimeters, and 2 kilograms or even 1 kilogram, right? So maybe like 2 pounds. You could see that air resistance matters a little bit, but our assumption of ignoring air resistance is not outrageous, because we could see for a lot of objects, we're actually going to get pretty similar curves there. All right. Good questions. Other questions?
I'm interested to see how it works mathematically. Are we going to combine those two formulas?
So this is what's cool. These formulas here, we don't need to combine them. The idea is, this is what's cool about it. Nothing is different. You already know how to do this problem. Imagine the X is like the cop, and let's say that the X is like the speeder, where acceleration was 0, maybe, and red is, or the Y direction, is like the cop. They both travel for the same amount of time. It's going in the X and the Y. This one's got an acceleration, that one doesn't. It's a very similar problem to that. And so, yeah, that's the math. Chapter's done. Maybe we should try a few practice problems though, huh? So what I'd like to do is first start out doing some standard projectile problems, and then we'll go to those kinds where there's acceleration both in the X and Y versus just in the Y. Excuse me. Oh. So let's take a look at page 72 in your book, okay? Oh, I closed out the, let me get it back open here. Right here. Okay, so again, page 72. All right, and so let's briefly go through this. Normally, when you're doing a problem like this, there are some assumptions we make. So this is a standard projectile problem. Not every problem is standard, but if you hear me say it's a standard projectile problem, you should assume this. Number one, air resistance is negligible. Okay. Number two, we're going to put our coordinate system basically right here, directly under the ball. Okay. If the ball started at the ground, they would be right at the origin. The idea is this is X and this is Y. That marker's really fat. But notice X initial would equal 0. Well, if X initial is equal to 0, delta X is the same thing as X final. And then why don't we just call all of those things just X? So rather than always having to write X initial, X initial, X initial, we're just going to assume the ball starts at X equals 0 and then just call X all the time. We're also going to assume the acceleration is 0 because gravity points straight down. This is the other half of that. Gravity points straight down. So the acceleration due to gravity is negative with magnitude G. G is positive 9.8. The negative comes from the direction, right? Acceleration is G downwards. So A sub Y is negative G. Now, so there's that part. Let me get a little bit of, how about a blue here? Notice this would be the initial velocity in the X, and this would be the initial velocity in the Y. Right? Well, I could see that this one, this V initial X, is adjacent to theta. That's where I get V initial cosine theta. Look carefully at this, right? V initial is equal to V. V initial X is not the same thing as V initial. V initial is the initial speed. This part here is essentially the X part. Cosine theta says just get the component along the x-axis. So it is wrong. You do not want to write. So this is bad here. V initial X cosine theta is wrong. Sometimes students will put both the subscript X and the cosine theta. That is bad. No, bad. All right. Now, similarly, you can see this V initial Y. That's going to be a sine theta. Now notice I put a plus or minus in here. You could use a negative sign if it's moving downwards, right? Similarly, if this thing is going from this height down here, delta y is not h. Delta y is going to equal distance h in the negative j hat. And so remember, this has an implied j hat on it, right? Okay, so far, hopefully that makes some sense. And then maybe I'll mention this. You might recognize this equation right here. This is delta y equals v initial y t plus 1/2 at squared, a sub y. Make sure you feel good about it. This, when I split it out, I just move the y initial over. V initial y right here is that. And A sub y is this negative g. So I'll pause there for a second. I guess you could see where this other one comes from, right here too, and right here. This is the same as our standard equations, except we use A sub y equals negative g. Okay? Nah, whatever, you get the idea. It's right there. All right. Finally, we've got this, all right. So I'm going to pause for a second and see if there's any questions on that.
So you would initially, so in a problem, you'll be given a vector that's going in the x and y direction, and then so you got to figure out, you got to separate those two vectors by using the cosine and sine theta respectively, right? I think that's what you're saying. And then you just simply plug those into the equation.
Yes. So, yep, that's it. So notice we do chapter 3. You know how to take a vector and split it up, and then just take the parts of the vector and shove it in here, turn the crank, and you solve for something. Got it? What do you think? Does that kind of make some sense? We're basically building on everything. There's a couple more pieces in here. Esteban, did that address your question?
Yes, it did. I'm just trying to put it all together in my head.
You won't get it until we do actual problems. So just be patient here while I kind of introduce it. This would be the final velocity in the x direction. This would be the final velocity in the y direction. And this would be the final velocity. Now, I usually call this angle right here phi. That's not a theta. Theta has a horizontal line. Phi has a vertical line. All right. Now, the idea here is you could see this is the final speed and angle comprise the velocity. This is the magnitude. This is the direction. And remember, when a physicist says impact, we really mean the instant just before impact, right? So just before it hits, this is how fast it's moving, and this is the direction it's moving. And notice it's a negative angle in this case, but yeah, generally speaking, we can avoid that just like we did in chapter 3 by drawing or being very clear with some words in there. All right. Now, I'll mention one other thing. In this problem, T, Memo, can you tell Nick I'm in class here? T is equal to X over, let's see, was it V initial cos theta? Right? If you take this, let me put a circle around this in a different color here. How about this? If you take this equation right here and shove it in both here and here, you get this equation. So if you're wondering where this last equation comes from, it's basically the same as that first equation, but solved. I eliminated t and plugged in what x. I basically solved for y as a function of x instead of y as a function of t. Now, to be clear, these both look like parabolas. Let me see here. Yeah. So these are both parabolas. The idea in this is quadratic in time. So it's talking about the way the vertical position only changes with time. This one is talking about y is quadratic in space. This is the one that describes the shape of the path. So if I could, maybe I should have done that in a different color. This one right here describes this shape. That parabola is described by this equation, not the upper parabola, not that t-squared parabola. All right. And then, does anyone remember what the velocity is at max height?
What do you mean?
I like that response. What's the velocity of a particle at max height? Let's see, we got the chat here. And so that was the answer I was looking for, Freud, and it happens to be wrong. Remember, that was true in the last chapter. So what Freud said, he said, isn't 0 at max height? Absolutely, for a chapter 2 problem. In general, that's not true. Take a look at this. At max height, you're still going to be moving in the x, but you're not moving in the y. So the best way to say it now is v final y, not v final y equals 0 at max height. So watch out for that. Everybody likes to think the velocity is 0 at max height, but it's only 0 in the y direction. All right. So, all right. And let's take a look at that. We've got a simulation right here, right? Right. So when I fire this thing, let's look at the velocity. And this time, let's not look at the components. Let's look at the velocity and the acceleration. Here we go. As we fire this thing, the velocity is the green arrow. It never goes to 0. Right? If we fire that again, right, the green arrow is all in the x direction at the top. Let's look at the components instead of the total, right? I'm going to slow it down when it gets close to the top here. So now, as I step towards this, notice you have a negative velocity in the y direction. Sorry, a negative acceleration in the y direction. You have a positive velocity. Because those two are at odds, the vertical velocity is getting smaller, smaller, and then right at the top, right there, notice there's basically no vertical, but the horizontal is still there. And now we should start to see the vertical get bigger. Now that the vertical velocity and the acceleration are pointed the same direction, it gets bigger and bigger. It's speeding up. Vy is getting more and more negative. And so notice, if we switch to total, notice the velocity is tangent to the curve. And so right there, as it impacts, just before impact, let's see. This is that impact angle I was talking about, right before impact. I think that's pretty good for getting a feel for this anyways, hopefully. What do you think? Should we try and do a problem really quick? We got 15 minutes. Let's look at 4.8 on page 73. Okay, I'll screen share real quick. Oh yeah, if you want, I forgot this in the last class too. I want to mention something really quick before we do that. There's problems with level ground. That's very different than what we've been talking about here. Standard projectiles need not have equal launch and impact positions, right? Down here, we have equal elevation. These are special problems where you get, in a special case of a level ground problems, these extra facts apply. I try not to do level ground problems on tests just because people try to memorize their way out of this and use these rules, and they usually don't know how to use them correctly for non-level ground. These rules just don't apply for non-level ground. All right, and again, you probably already noticed, sometimes I'm going to use the upper equation. Basically, look at this. Sometimes I'm going to write the equations with the g in it, and sometimes I'm going to write it with the ay in it. Sometimes it's going to have the y final and y initial on opposite sides. Sometimes it's going to have the delta y. I assume you can use both. There we go. That's enough on that. All right. So let's take a look at this one. All right. So I'm going to draw it up. You go ahead, draw it up. Whoops. Yeah, 4.8. Okay. So this is just looking at that problem. That angle's theta. There we go. So part A, whoops, it's asking about the determine max height, right? Well, let's not overthink this. We're going to do our same procedure, only now we're going to have it twice. It's like a cop and a speeder problem. Once for the X direction, once for the Y direction. You could think of the X direction as being the snail or the speeder, and the vertical direction as being like the cop, or vice versa. It doesn't matter, whichever you want to think about it.
Would T be the same on both, right? So you don't have
Exactly.
to put TX or TY.
Exactly. T is a shared variable because it's moving horizontally for the same amount of time it's moving vertically. So I'm not even going to write it. Just do it two separate ways here. All right, we're supposed to be going to the max height. All right. So let's go through this. Do I know delta X? I don't think so. V initial X. Do we know that?
It would be V cosine theta.
V cosine, right? So notice if I'm on this side right here, wouldn't that be V cosine theta because it's adjacent? I don't know if you can see that very well. We'll scoot up for a minute. Okay. So this side would be V cos. This side would be V sine. Well, I might as well grab that. Oh, go ahead. What were you going to say?
Is the only acceleration here is gravity?
Yeah, and so unless you are otherwise told, you should assume the only acceleration for a standard projectile, right? If you kick a ball, we're going to ignore air resistance unless I specifically tell you to do it. And of course, for this class and most classes, we're going to ignore it because it's really hard. All right. I can show you how to do it with a computer code, but it's a little harder to do it here. And we need to understand forces first. So yeah, we'll save that for later. So yes, a sub x is 0, a sub y is negative g. We're assuming that this is kind of our coordinate system. That's our y direction. This is our x direction. That's the assumptions. All right. Oh, I think you told me this was v cos already. What's v final x?
I don't know.
Oh, go ahead.
But I would think is B final Y 0?
Yeah, because we're at max height. So somebody else, if a sub x is 0, how much is the velocity in the x going to change? If ax is 0, what do you think? Oh, somebody might have put it in the chat there. Okay. Oh, maybe not.
Is it the same?
Yeah, excellent. Nice job. And then time, did they tell us the time? I didn't see it. No. How about what's delta y? Do we know that?
I don't think so.
No, that's what we're looking for. We're looking for the max height. Isn't that going to be delta y in this particular case? That's what we're looking for. All right. Now, from experience, anytime the x is 0, there's only one equation worth writing. We know, maybe I'll put the time here. We still don't know that. I do know that delta x is equal to v initial x times time, right? Or if you wanted to, you could write this out. If we say that ax is 0, this thing drops out and all we get is this. Distance equals rate times time when acceleration is 0. Now, if I wanted to, I could do, but again, this is what we were just saying. If a sub x is 0, the final and the initial are equal. So we already used that. We already know that. We don't need that. And then the v squared equation gives us the same thing. So now, how about over here on the y direction? So I'm going to get rid of this. So there's our x equation. When I do this, close enough. All right. So now, in this case, I'm going to number these equations so we could talk a little bit easier over the internet. So we were supposed to get the max height. Esteban's been chiming in a lot. I'm going to ask him to kind of wait it out here and just let other people try to answer. But take a guess. Which of these equations seems like the best one to use? Take a minute to look at them and I'll get a sip here. Everybody wait a minute and then I'll ask you again. I'll give you just a second to think here. All right. So we're looking for the max height. Does one of these equations help us get that most rapidly? If so, which one? Or any strategy? What do you think? What goes on in your brain? Somebody other than Esteban.
Equation 2.
Okay, equation 2. Let's take a look at it. Do we know the time?
No.
How could you get the time?
Well, we could use equation 3 to get the time.
3. That would work. And so that is one common strategy. You use equation 3 to get the time. You plug it into there. You got it. What's the other strategy that kind of jumps out?
Use equation for number 4.
Use equation 4. Know this, know this, know this, know this. You get it right away. So it turns out for max height problems, reach for the v squared equation first. Sometimes it'll get something for you. Okay. And then you could, obviously this way is how you get the time. And then typically what I do is I use this to check these two answers. So I could use this delta y and that t and see if they give me the same answers. Or when I plug that t into there, do I get the same answer? All right, that's good. All right, let's see where we're at, 333. So I guess that's parts A and B from there. And so just in the interest of time, what should you guys do? This was just a brief introduction. You're probably pretty confused, maybe starting to get a little bit of a feeling for it. And then what I would do for the next class period, if you look at this page, zoom. All the problems on this page are pretty much level ground problems. They're the easiest problems in 2D motion. Now, this one you don't have to do because it requires calculus, and you're not supposed to be doing calculus in this class. Gee, I wonder what we'll do next semester. That said, on this page and read a book by the next class period, you should be in great shape and be setting yourself up for success. All right. Now, as you can see, these are more like test level questions on this page where it's not level ground, but you're just starting. You're not going to be good at those if you can't practice with the easy questions first. All right. So, and then after a couple of days, maybe at the end of the next day, we'll get into this one where, notice, I'll show you how to handle problems when you do have AX, or here's a drone, right? So we could do problems that do have AX later. Let's just start out with AX equals 0. Make sure you get that. And then it should be easy to add in AX after the fact. That's our goal. Any questions about that?